center of mass, coordinate and center of mass momentum, sum of these two. So string moves around in the space-time with this, and it fluctuates with the second part, which represents the oscillation. So it oscillates via the second part, sum of these two, and it moves around with the sum of these two. All right? Okay. So, and just to give you an idea that this kind of a thing, so for a string, I mean, this is just a demonstration for a free particle. So that this x mu, what have I done? I have made a mistake. I should not have written capital X. This must be small x. These are small x, which I'm saying coordinates. Okay. These are the string coordinates. These are our string fields. They are the fields that correspond to the one-dimensional object called a string. Okay. And we have not yet considered whether we are going into open or closed string. We now look at it. And by looking at them, we can impose a few things. So let me just remove this part. Now, without going into mathematical derivations of some of these things, it may be enough to recap that, for example, here this k is the wave number of the wave vector. Okay, here this k is the wave number of the wave vector. It need not be an integer, but we will see whatever boundary conditions tell us. Okay, so in the now, for example, we go to open strings with Neumann boundary conditions. Neumann boundary conditions at both the ends, which means at sigma equal to 0 and at sigma equal to pi. Okay. So, and what is the condition? Neumann condition. They tell us the boundary conditions. The x prime mu equal to 0. So what you do is you consider del sigma x mu equals to 0. Okay, the space derivative of x mu. Space derivative of x mu has to vanish at sigma equal to 0 and at sigma equal to pi. If we impose at both the ends the same n. Okay, so I would be right now considering only n and dd, but you can also consider nd and dn. Okay, so you take x mu, take its sigma derivative and equate it to 0. And this would give me, let me first do it at sigma equal to 0, then this would be del sigma x mu L at sigma equal to 0 plus, no problem, this is del sigma f mu r at sigma equals to 0. And if I do that, then what I find is that 0 equals to Is it from here? Coming from outside? Oh, okay, fine. I'm happy. I thought something was wrong with one of these cameras, but it's okay. If it's coming from there, that's fine. So, all right. So what are we doing? We consider x mu, which is the sum of x mu n and x mu r, and we want to take the space derivative of x mu, and we want to make it at sigma equals to 0. Okay? So we are applying the Neumann boundary condition at one end, at sigma equals to 0. And if you do that, in this I have omitted the intermediate steps, which are trivial, and they are step by step also given in my earlier lectures. I noticed. So what we get is this and this. So what happens that both the terms will have to vanish separately. If the left hand side is 0, so I would get PL mu equal to PR mu, and I would get alpha K mu equal to beta mu. This would be the outcome. So outcome is x no PL mu equal to PR mu. And the other outcome is alpha mu K is beta mu. This is the outcome. Okay. Now, when you apply this condition at this point, I have written at sigma equals to 0. Okay, right now I am doing it at sigma equal to 0. Now, so can I, maybe I need to remove this part. All right. Now, I would like it to vanish at sigma equals to pi. At sigma equals to pi, and we again skip the mathematical details, and when you demand this thing to vanish, the space derivative of x mu to vanish at sigma equals to pi, then we arrive at k equal to n equal to integer. That is the only outcome. So the other outcome is that k equals to maybe n or whatever, but k is an integer. Okay, that is the outcome if we apply the Neumann boundary condition at the other end also. At sigma equal to pi also, if we apply, we get this. And you see, just a remark, in fact, PL mu equal to PR mu always holds for a non-compactified dimension. So if all your dimensions are non-compactified, this would always hold. Okay, PL mu equal to PR mu. Also, actually, for open strings, also for closed strings, we will go step by step. Just to recap the main results, what are we doing, what are we having, okay? Skipping some of the details which otherwise it will go on into several lectures. So this is, now, if you apply if you consider the open string with DD boundary, but at both ends, DD, okay? And then what you would find, you would like this to vanish, or you would like this also implies, okay? So this is also built into that, okay? So x mu does not change with time. That is our Dirichlet boundary condition. And in this case, what you will find is, I mentioned you the result. Here, what is the result? The result is for that PL mu is equal to minus PR mu. This is one outcome, and alpha K mu is minus beta mu K, and when you apply it at the other end, so these are the two net outcomes. That at one end you get this and this, and by applying this reachable boundary condition, you get K equal to an integer. Now, so what happens here? This is in conflict with P mu L for a non compactified dimension. You see, no, PL mu equal to minus PR mu is in conflict with the case for the non-compactified dimensions. For non-compactified dimensions, for